Hi, everyone. You're listening back in time for a recorded talk about the cosmic ring of fire, a recent publication of ours. So I would like to start this talk by sharing a skinny relation. The x-axis is knowledge, how much we know about stuff. The y-axis is surprise, how surprised we're going to be when knowing about something. So usually the more you know about something, the less surprised you're going to be. Studies have found that the process of satisfying our curiosity through gaining knowledge is associated with pleasure. Scientists usually lie on the bottom right of the diagram and have a narrow dynamic range of getting pleasure. And that is the primary reason to propel us to push the frontiers of knowledge so that we can reset the baseline of surprise. So this talk is going to be about ring galaxies, and if you already know everything about ring galaxies, then the dynamical range for pleasure is very small, in which case you can pay extra attention on the uncertain range of our knowledge. So ring galaxies, we do know a lot about them from the nearby universe. So 50% of spiral galaxies nearby have rings or partial rings. We call them ring galaxies because they are usually associated with some sort of orbital resonance triggered by bars, spiral arms, or ovals. On the day of our published article, we actually got this surprise. So one of the pundits of ring galaxies, Ram Buddha, wrote us a very nice commentary and review article about ring galaxies. And if you want to know more about ring galaxies, I'd refer to Buddha's work in this regard. This talk is going to be focusing on collisional ring galaxies. Why are collisional ring galaxies so rare? They're rare because head-on collisions are rare. It's almost as if the universe is hosting a cosmic Olympic shooting game, and those who can hit the bullseye wins the title of collisional ring galaxies. And the rings you're seeing here is actually density waves. And collisional ring galaxies are considered one of the best laboratories to study density waves and how they trigger star formation. And this is much simpler than spiral arms, whose origin is still highly debated. So people think that we should find more of these collisional ring galaxies at high redshift simply because there are more collisions in the past. However, there are very limited observations at high redshift. Essentially, only 2 studies focusing on observations of ring galaxies at high redshift, and they are with limited information. Basically, only redshift and image are reported for those ring galaxies. So what you're seeing here is the density rate or volume density rate of ring galaxies as a function of redshift. This is a study led by Ahmed. When I met Claudia and Ahmed 2 years ago, we were both surprised when we compared the new Eagle simulation prediction of the volume density of ring galaxies with our newly found ring galaxy, the highest redshift collision ring galaxy, the ring of fire, as you can see here. We found that the volume density of ring galaxies at Z02 is as rare as they are today. And we speculated that the lack of thin disks as the aiming board at high redshift, as well as the lack of a supportive grouping environment, might have caused the lack of collisional ring galaxies despite the increase of merger rate. Of course, there seems to be a slight increase in collisional ring galaxies at the epoch of thin disk formation, but that is going to be the story for another talk. And also why do collisional ring galaxies require a thin disk in order to form the density wave? That is also the story for another talk. So here is the ring galaxy shown in different color bands. Is our existing knowledge of ring galaxy sufficient to explain the observational data of this ring galaxy? We first ruled out this ring galaxy as a ringed galaxy simply because it's going to be too large. The normal in terms of the regular size galaxies at redshift 2 of a similar mass is going to be as very much like this galaxy, whereas this ring galaxy is too big for a redshift 2 galaxy if they are isolated. For example, comparing with our Milky Way, it's almost twice larger than the Milky Way at redshift 2. And if it's a ringed galaxy, it's going to be hosting a huge bar as large as 5 kpc at redshift 2. This is going to challenge galaxy formation and simulation models more severely than the recently found Wolfram disk at redshift 4. And we think that a collisional ring scenario is more consistent with the data, and the large size can be explained through the collision. We actually found 3 pieces of key evidence to support the collisional ring scenario. First is that it has a companion that is very close by and interacting with the ring galaxy. And second is that we're able to derive a large radial velocity of this ring. So this ring is rotating and also moving very fast radially, most likely expanding. And the third piece of evidence is that we're able to find the off-center nucleus, the knockout nucleus, through the collision. And this would be a perfect target for JWST follow-up in the more redder bands. So we think a collisional ring galaxy is the origin of this galaxy. But is our existing knowledge of collisional ring galaxies sufficient to explain what we observed here? The answer is not without revision. What you're seeing here is the star formation rate as a function of stellar mass, the so-called main sequence. So most of the nearby collisional rings lie above the main sequence of their peers. They're forming stars much quicker than isolated spirals. Whereas this ring of fire is not burning as much as we expected it would be. In fact, it's actually forming stars much slower than its companion galaxy, which has a much slower, slightly lower stellar mass. One of the explanations is that this ring could be a secondary ring. So, when you trigger density width, you actually get consecutive rings, just like the secondary ring of the Carwell galaxy. So we can do the exercise. We can put Carwell galaxy to high redshift and let it evolve to the brighter end through this main sequence evolution. And here is what it looks like. Still, the secondary ring of the Carwell is nothing compared to our ring of fire galaxy. And also, what's up with this fuzzy stuff outside of the ring? So usually, if you see a little bit of light outside of the collisional ring galaxy, it's usually induced by tidal tails. The brightest fluffy disk outside of the ring in the nearby universes are arc 147. And similarly, we can put arc 147 to high redshift and let it evolve to the brighter side through the main sequence relation. And here's what it looks like. You do not see such a large extended and bright disk outside of arc 147. So a lot of work are still required to fully resolve the puzzle of this ring galaxy. And we got a little bit of hint from the EGO simulations. So you're seeing the highest redshift collisional ring galaxy from the EGO simulation. So what we found is that the mini satellites around this ring galaxy, which you usually don't see in the nearby universe, can scatter the stars outside of the ring. 50% of them can be scattered out. So that might be a cause of the extended light outside of the ring. However, we need finer time steps, better resolution simulations to fully understand these systems. But the good news is we got some new data from ECWI. So hopefully the rest of the UV spectrum can give us a better understanding of the star formation history and also related to what density wave is doing to this ring galaxy. Sorry, that's my alarm. The also equally exciting is that we have found a gravitational lens collisional ring galaxy at high redshift. It's going to provide us a sharper view of what's going on with the collisional rings at high redshift. So stay tuned. Finally, I would love to highlight that this work is a natural collaboration amongst different experts within Astro3D. In addition to my co-authors, I would like to give special thanks to Lars Lindqvist for letting me study him in the beginning of this study for the scenario of a collapsing ring, and Josh for his insight on the bar formation, and Emily for her generous sharing of the positional angle from the CMOS 3D data of this galaxy, and Marianne for discussing the difference between mergers and collision rates, and Yesa for sharing his experiences with the journal. And that's all from me. I hope you enjoy the rest of the science meeting. Thank you very much. Bye.